is more on reactions, whereby you have more than one reactions. Okay, so this topic is quite lengthy, whereby maybe I need we will, what do you call it, I will cover all the topics, number 6, about 2 weeks. Okay, so we will be having part 1 for today, and then part 2 for this Thursday, and then part 3 for the next the following Tuesday, and for the Thursday I will allocate 2 hours for the tutorial. Okay, so don't want to go too rush for this topic, alright, to ensure that you really understand this topic lah before we proceed to the subsequent topic, alright, which is chapter number 8, topic number 7, sorry, number 7 tu dah kira last lah tu. Okay, so let me share the slide. Okay, you may find the lecture notes in the Teams. Okay, jap, I tak share lagi kot slide. Ni jap, tak share screen. Okay, I think I have to switch off the camera sebab takut ada lagging nanti during the lecture, internet. Okay. Okay, are you able to see my screen right now?
Yes, Doctor.
Oh, okay, good. Alright. Okay. Sekejap, I letak ni. Okay, so this is the new topic that you're going to learn. Alright, which is the design of multiple reactions. Okay, let's see if there is a lagging from my side. Please notify me. Okay, you just interrupt me. Okay, so this one means that you will learn about more than one reaction. Alright, in more than one reaction in one reactor. Okay, and here also you will learn a new term. Okay, which is desired and undesired. Okay, so from here, multiple reaction, you need to familiar with this term, which is D. Alright, is defined as desired reaction. Okay, and then we have a U, actually is referring to undesired reaction. Okay, of course, if we have a multiple reaction, okay, let's say we have one reaction, and then second reaction, and third reaction. Okay, so you will have a which one which is much more desirable. Okay, so between these, so you have to select lah. Okay, all right. So lecture outline. Okay, for today you will learn about concept of selectivity and yield. Okay, and then followed by 6.2, which is Rectus selection based on selectivity and yield. Okay, so from the selectivity, you have to choose lah what kind of Rector you want to select. Alright, whether it is CSTR or whether it is a PFR or batch, okay, and so on. Okay, so today we will cover 6.1 and 6.2. Alright, and then followed by parallel reactions. Okay, this one we will cover this Thursday, and this would be the last part, series reactions. Okay. Okay, so at the end of this chapter, the student should be able to describe terminologies related to multiple reactions, namely selectivity and yield. Okay, so you have S here, and then we have Y, yield here. Okay, as a yield. And then classify types of multiple reactions. Okay, whether it is a parallel, okay, whether it is a series reactions, independent, or complex. Okay, so these are 4 kind of reaction you will learn, and then you need to know how to describe parallel and series reactions, as well as apply the algorithm for solution of reaction design that involve multiple reaction. Okay, so this one actually for complex here, okay, you need to use software, okay, to solve it. Okay, for example, we have a MATLAB or Polymath. Okay, so this one, you will use this one for assignment number 2. Okay, you don't have to use for final assessment because final assessment for this semester is not a 24 hours test. Okay, it's only 2 hours test. Okay, so this is parallel reactions. Okay, or we call it as competing reaction. Okay, dia akan compete lah to each other. Okay, whereby the same reactant here but produce a different product. Okay, so this is A to B, reactant A forming B, and reactant A forming C. Okay, so it has its own rate constant here. Alright, and this reaction happens simultaneously. Okay, at the same time lah dia berlakunya. Okay, and then we have a series reactions. Okay, series ni dia bersiri lah. Okay, we have A to B and then B to C. Okay, so usually B would become the desired product. Okay, and C actually usually this will we will categorize as undesired. Okay, so that's why you need to control the reaction so that the B will not proceed to form to C. Okay, so C usually is a byproduct lah, we call it as a side product. Okay, we want to get the maximum B, so we have to make sure this B will not be converted into other product. Okay, for example, becoming C. Okay, so kita nak ni lah, kita try to get the highest possible lah for this desired product. Okay, and then we have independent reaction whereby if you can see the parallel, it is using the same reactant, but for this one is independent. Okay, so dia tak bergantung. Alright, so A to C and then B to D. Okay, this is a different one. And then we have a complex one. Okay, so complex ni dia bercampur-campur. Okay, for example, we have A to B and then A to C. Okay, so this is the parallel one. Alright, and then after this what they call it, parallel reaction happen, the B will combine with the C in order to form a new product, which is D. Okay, so this is we categorize it as the complex reactions. Okay, and then we have another one which A forming B and C, and then the C here, alright, which is the side product, will gabung balik, will combine back with the reactant A in order to form a new product D. Okay. Okay, so parallel, which is we call as competing reactions. Reactant is consumed by two different reaction pathway to form different products. Okay, so ni ada dua lah pathway, which is we have a first equation and then we have a two equation. I nak kena move benda ni. Macam mana I nak minimize? Oh, minimize ni. Okay. Alright, so reactant is consumed by two different reaction pathway to form different products. For example, we have an oxidation of ethylene. Alright, this is ethylene. Okay, to ethylene dioxide. Okay, so this is ethylene dioxide. Okay, dia attach oxygen punya ni atom here while avoiding complete combustion to carbon dioxide and water. Okay, so we have a parallel here, which is this one towards this, we have K1, and then this one towards carbon dioxide and H2O. Okay, so from here, the desired one will be the to have a ethylene dioxide as a main product. Okay, so this one is the undesired one lah. Okay, and then we have a series reaction, which is a consecutive. Okay, consecutive reaction, reactant to form an intermediate product which react further to form another product. Okay, so example A to B equals to C. Okay, so for example, reaction of ethylene dioxide. Okay, ethylene dioxide ni, okay, plus with the ammonia here. Alright, to form a mono. Okay, this is mono. Alright, satu. And this is a di. And this is 3. Okay, 3 ethanol amine. Here, okay. So this is a series. Okay. So from here, actually, what you need to know is how you control the desired one. Okay, so for example, you will look at the suitable operating condition. Okay, kita akan tengok pada operating condition. Macam mana kita nak control, nak maximizekan desirable ni lah. Okay, for example, kita tengok pada T. Okay, we have to look at the P. And then we look at the concentration and so on. Okay, so remember pressure ni, okay, changes usually they occur dekat gas sahaja. Okay, so for example soalan macam MTA hari tu, saya ada tanya apa pressure change tu untuk liquid system. So sepatutnya dia tak ada change pressure tu. Okay, sebab dia dalam liquid, dia bukan compressible, dia incompressible. Okay, so kalau dia incompressible means that there is no change of ni lah pressure. Okay, selalunya dalam liquid lah. Alright, and then we have another one. Okay, kita kena tengok dari segi what kind of suitable reactors to be used. Suitable reactor. Okay, so this is how we determine lah this selection ataupun selectivity. Okay. Of multiple reactions, okay, complex reaction of parallel and series, couple of reaction that provide a combination of both series and parallel reactions. Okay, so we have A to B, okay, A to C. Okay, so for example, we have this one is ethanol. Okay, so this is the ethanol. Okay, so the ethanol can produce C2H4 ethane, alright, as well as the CH3CHO. Okay, which is butadiene. Alright, this. Okay, and then from here, alright, the product here and another product, alright, which is B and C. Okay, so this is the B and C. Okay, will produce another one, which is a D here. Alright, butadiene. Okay, and then we have independent reactions. Okay, reaction that occurs at the same time but neither the product nor the reactant react with themselves or one another. Okay, for example, so ini dia tak, reaction 1 and reaction 2 tak ada kaitan lah. Okay, so cracking of crude oil to form gasoline where two of many reactions occurring are. Okay, so daripada sini dia tak akan usik reactant lah untuk dua-dua reaction ni. Okay, masing-masing ada sendiri punya reactant. Okay, so types of multiple reaction, which of the following reaction pathway best describe the data? Okay, so if you can see, we have a concentration here and we have a time here. Okay, you need to look at one by one. Okay, which one is suitable, A, B, or C? Okay, for example, you know that when A decline here, all right, the B will produce. Okay, and at the same time, when A decline here, all right, C will produce at one point. Alright, here, okay, dia akan produce at one point here, and then it decrease, alright, because the concentration of D is increasing, means that the D is forming, alright, so means that A ni, okay, dia akan menghasilkan B sebab A akan berkurangan, reactant dah digunakan, so dia akan produce ke B. Okay, at the same time, if you can see, A ni juga bila dia menurun, alright, kalau you nampak B dengan C ni dia increasing at the same time here. Okay, so means that dia berlakunya parallel. Alright, remember syarat parallel adalah dia akan happen simultaneously, okay, which is A akan produce juga kepada C, okay, tapi D ni dia tak berkaitan. Kalau you tengok D ni dia start increasing bila? Dia start increasing bila C menurun. Means that C as a reactant will be used to form D. Okay, so the answer would be B. Okay, get it, everyone? Okay, so the intermediate product is the C lah. Ni, okay. Okay, then types of multiple reactions, we have A to B plus C. Alright, remember rate of reactions, negative RA is equals to KCA. Okay, so if you have a parallel reactions here, okay, A to B. Okay, so let's say this is K1, rate constant of 1, and this is rate constant of 2. Okay, so it becoming negative Ra K1Ca. Okay, tengok dia tengok pada reactant sahaja. Okay. Okay, and then we have this one. Okay, negative Ra. Okay, is equals to K2Ca kuasa 2. Order of reaction dia dah 2. Okay. Alright, so bila parallel, you have to gabungkan dia, combinekan dia. You need to plus it. Okay, sebab K1 dengan K2 ni adalah berkaitan dengan A. Okay, so dia kena bercampurkan lah, combinekan dia. So we have a K1Ca plus with the K2Ca2. Okay, so this assume elementary red law. Alright, then we have A to B and then B to C. Okay, so from here, you can tengok sekarang ni, dua equation ni dia adalah dependent on the B, compound B. Okay, not A. Alright, so kita boleh buat dia as a relative rate of reaction. Remember yang negative Ra is equal to negative Rb or equals to Rc equal to Rd. Okay, per dengan stoichiometric coefficient lah. Alright, so this one is negative Ra. Okay, katakan this is K3 and this is K4. Okay, so negative Ra is equals to Rb1. Okay, kalau ni B dia akan jadi positif lah. Kalau ini as a reactant, okay. Sorry, dia adalah product formation, so dia akan positif here. Okay, so equal to K3Ca. Okay, so for K untuk Rb2 pula, okay, which is this one. Okay, so this one kalau kita letakkan dia sebagai rate of reaction as a reactant, so it should be negative Rb2 is equals to K4, alright, Cb. Okay. Alright, tapi kalau kita inversekan dia, okay, it will be Rb2 negative K4 Cb. Okay, so the Rb net, which is Rb1 plus with the Rb2. Okay, remember ni yang you belajar masa topik number 5 yang last to subchapter. Okay, so daripada situ you just combinekan dia. Okay, what is Rb1? Rb1 is K3Ca plus with Rb2. Remember kita nak dapatkan positif saja, so minus K4Cb. Alright, so careful with the sign here. Okay, don't get mixed up. Okay, as long you follow the order red law, it should be okay. Okay, mana satu positif, mana negatif. Alright, so proceed to 6.1. Okay, so hari ni memang you belajar konsep saja, macam tak ada pengiraan sangat lah. Okay, so concept of desired and undesired reaction. This is D and this is U and S is capital and Y. Okay, so desired and undesired reaction, reactants are consumed in the formation of a desired product, apa tu, as D, and the formation of undesired product, okay, U, in a competing or side reactions. Okay, so let's say we have a parallel reactions, okay, which is A to form D. Alright, so this is the desired one. Okay, this you want to get the main product. Okay, but during the process also, it can cause a side reaction ataupun another reactions. Okay, happen simultaneously whereby A can be converted into another product which is undesired. Okay, so what you need to do is you need to maximize this concentration and lower down or minimize this undesired. Okay, and in case of series of reactions, okay, we have a A to D to U, right? So from here we want to maximize the D, alright, and try to avoid D to be converted into U. Okay, so we want to minimize the formation of U and maximize. Okay, so this one to minimize the formation of U and maximize the formation of D, because the greater the amount of undesired product formed, the greater the cost of separating the undesired U from desired product D. Okay, so usually we have a main reaction which occur in the reactor system. Okay, so usually they akan produce lah. Okay, for example, we have a D and U. Okay, so in order to get the high purity, alright, kita kena separatekan D and U. Okay, of course, if you want to separate it, you have to proceed to the next unit operation. Okay, we call it as separator lah. So it can be a distillation column, it can be a normal separator, depends lah pada your design, okay, design of the process tu. Okay, so bila dia ada extra equipment here, it will incur extra cost. Okay, so that's why as a chemical engineer, we try to avoid lah undesired product form from the reactions. Okay, and let's say this is a general flow sheet for a process with one reactor system. Okay, so we have a feed here, okay, separation system, alright, and then we mix here. Okay, usually for the reactor system kita nak single what they call it, single inlet sahaja. Okay, that's why kalau dalam soalan tu kalau ada mixer here, you kena cari the new V0 here. Okay, you cannot use from this from the mixer one. Okay, sebab mixer ni dia ada more than one inlet. Okay, so you have to combine, recalculate and to get the V0, alright, the new V0. Okay, so this the combined feed will go to the reactor system, and then there is a effluent from the reactor. Okay, so from here there is a separation system to separate between the product and byproduct, okay, in term of the vapor ataupun liquid. Okay, so liquid ni pergi bawah lah sebab dia lagi berat. Okay, vapor dia akan pergi atas. Okay, for example like distillation column. Alright, and then some of the product yang dia tak convert habis, it will be recycled back to the mixer. Okay, untuk convert into the product balik semula. And then some of the liquid also can be what they call it, recycle here. So case 1, okay, highly efficient and cost reactor, very little of undesired product you. Okay, so case 1 ni adalah untuk berkaitan dengan kita nak efficient punya system and also costly reactor. Okay, so means that kita akan produce a very little of undesired product you. Okay, means that kalau highly efficient means that D kita adalah okay. Okay, dia dah maximize dah D dekat sini sebab dia very efficient. Alright, and the separation cost should be quite low. Okay, so bila D dah tinggi means that U kita dah minimize. Alright, so to separate it kita boleh ada low cost lah, alright, instead of high cost. Okay, and then we have another case number 2, which is inexpensive and inefficient reactor. Okay, so kalau reactor ni kita guna yang cap ayam punya kan, alright, ataupun inefficient, dia tak convert habis, alright, for example dia convert less than 70% ke, okay, so separation cost will be quite high lah sebab in order to separate between the D and U. Okay, so normally as the cost of reaction system increase in the attempt to minimize U, the cost of separating U from D decreases. Okay, so dia macam apa, inversely proportional. Okay, so for example reactor cost makin tinggi, alright, so the separator cost would be lower down. Okay, so concept of selectivity. Okay, so you kena ingatlah what is selectivity. Alright, so selectivity tells us how one product is favored over another when we have multiple reactions. Okay, there are two types of selectivity. Okay, so the first one is the instantaneous selectivity. Alright, this is number 1. Another one, okay, the red font ni is the overall selectivity. Okay, so nampaklah tanda ni. Okay, dia ada SD over U. Alright, so instantaneous selectivity of D with respect to U is the ratio of the rate of formation of D to the ratio of formation of U. Okay, means that as, okay, selectivity D, alright, over U is equals to rate of formation, which is the RD over dengan rate of formation of U. Okay, so daripada sini kita boleh expand lah what is rate law define, rate of reaction define as, katakan we have a A and B, which is K1 CA CB, okay, refer to this one, and then over with the K2 CA CB. Okay, so overall selectivity is defined in term of flow rate. Okay, so for overall ni dia adalah flow rate. Okay, so means that Dia lah in term of F. Alright, F capital. So what is it? S du, okay, remember overall dia ada tanda yang ni. Okay, D over U is equal to FD over FU. Okay, so FD is the exit molar flow rate of desired product. And FU is the exit molar flow rate of undesired product. Okay, remember F is equals to mole per time. Okay, for a batch reactor, the overall selectivity is given in term of the number of moles. Okay, ingat kalau untuk batch reactor adalah in term of N, capital N, which is ND over with the NU. Okay, right. So example 6-1. Okay, develop a relationship between SDU and SDU for CSTR. Okay, so we have instantaneous here. Instantaneous. And we have, this one is overall. Okay, so you have to develop what is SDU for RD over RU. Alright, and also SD over U is equals to FD over with the FU. Alright, so we know that R, okay, remember yang I cakap kalau kita ada rate of reaction, okay, for example we have negative RA, K, CA and so on lah. Okay, so this one will have the fixed unit. Okay, K ni nama pun constant, so means that K ni akan berubah depending on the RA dengan CA. Okay, so from here rate of reaction, okay, we define as concentration per time. Okay, remember unit untuk rate of reaction adalah concentration per time. Okay, so equals to, okay, you boleh kembangkan dia mole over with the V. Alright, V is volume times with the T. Okay, so this one is defined as F. Okay, so we have F over with the V. Okay, alright, remember concentration adalah mole per V. Okay, so from here we have F is equals to RV. Okay, so we have to do one by one sebab kita ada FD dengan FU. So FD is equals to RDV. And then, sekejap saya nak. Okay, ni dia. And then we have a FU is equals to RUV. Okay, so daripada situ, we have a SD over U. Okay, is equal to FD over FU is equals to RDV over dengan RUV. Okay, so daripada sini we have a RD over with RU. So sama juga kita akan dapat balik SD over U. Okay, so this is for CSTR. Okay, sebab apa? V ni adalah constant lah untuk CSTR. Okay, get it everyone? So far?
Okey, Doktor.
Okey, Allah, kenapa suara lemah saja? Semua dah breakfast ke belum? Okey, breakfast.
Minum
air je tadi.
Allah, minum air pula kesiannya. Okey, at least makanlah sekeping roti. Ingat, breakfast is the king of meal. Okey, alright. Okey, tak apa. Nanti pukul 12 bolehlah terus brunch lah. Okay, so we have another one. We have A to KD over KU. Berapa sekarang? 10:30. Okay, kalau kita habis awal, sebab hari ni sampai 30 slide sahaja. Okay, sekarang kita dah halfway dah ni. Okay, cayuk. Alright, so we have a negative RA. Okay, KD CA1 plus K2 CA2. Okay, remember kalau benda macam ni kita boleh as a RA net. Okay, so RD is equal to KD CA1A. Okay, RU is KU CA2A. Okay, so A ni adalah order of reactions ya. A adalah order of reaction. Okay, So daripada sini we want to maximize SDU. Okay, remember kita nak ada selectivity which is has a maximum D but minimum U. Okay, means that you need to get the RD tinggi, RU rendah, baru you dapat value of ST tinggi. Tapi kalau tiba-tiba, kalau you terbalikkan, RDU rendah, RU tinggi, S ni akan dapat rendah. Okay, so kita tanda tu. So kita nak yang tinggi. Alright? Okay, so from here, dia adalah KD ni. Okay, remember, ni dekat Arrhenius equation semua tu lah pun ada cerita. This K actually is referring to the function of the temperature as well as the concentration of reactant. Okay, so berdua factor ni lah dia bergantung. Okay, usually kita akan try to manipulate these two parameter lah in order to get high selectivity. Okay, so this one is equal to rate of formation of D over rate of formation of U. Okay, so rate of selectivity parameter here is equal to instantaneous selectivity SDU here. Okay, so sama dia. Right, so based on the ratio of reaction rate, okay, we have a yield at point instantaneous yield YD is defined as the ratio of the reaction rate of a given desired product to the reaction rate of the key reactant A. Okay, so sebelum ni kita belajar untuk S. Sekarang ni kita akan tengok pada what is Y. Okay, so Y ni actually is referring to YD. Okay, they akan refer back to the reaction rate. Okay, which is R. So it's equals to RD, okay, over with the key reactant A, which is the negative RA. Okay, so this actually reflects the what they call it efficiency of the reactions lah. So ni adalah sebenarnya reflects, yield ni adalah reflects pada the efficiency of the reaction. Okay, so this is what YD is equal to RD over negative RA. Okay, sama jugalah dengan sebenarnya SD over U is equal to RD over RU. Okay, so based on ratio of molar flow rate, okay, tadi ni adalah berdasarkan rate of reaction, okay, daripada R. Sekarang ni adalah ratio of molar rate, flow rate, okay, so it can become F dengan N. Okay, so dekat sini dia ada N versus dengan F, sebab N is referring to batch system and F is the flow system. Okay, so the overall yield is defined as the ratio of mole of desired product. Okay, so desired adalah D, so dia akan jadi ND ataupun FD lah, right, to the number of mole of the key reactant A that has been consumed. Okay, which is kalau has been consumed means that adalah N A naught minus filter NA. Okay, so this is what dia dah being consumed. Ataupun FA naught minus filter FA. Okay, so here you will have this one. Alright, yield of D, and then we have a yield of D in terms of the flow system. Okay, so similar to selectivity, the instantaneous yield and the overall yield are identical for a CSTR. Okay, so sama juga boleh applicable to CSTR. Alright. Okay everyone, nanti saya saya tekan satu lagi ni slide, kita rehat sekejap lepas tu. Alright. Okay, then we have a selectivity, how one product is favored over another when we have multiple reaction. Okay, so this is just a summary. Okay, you can look at this table. Alright, dia dah summarize according to instantaneous and also the overall. Alright, so for the selectivity instantaneous, yang bezanya adalah in term of symbol, and also this is rate of reaction, and this is for the flow molar flow rate. Okay, and then for the reaction yield pula, there are two definition, whether it can based on this one rate of reaction rate ataupun ratio of the molar flow rate. Okay, so this one is the flow rate of desired, and this one is the one that being consumed. Okay, so from here, okay, let's say we have A plus B equals to D, and then 1 plus B equals to U. Okay, so this is parallel or series? Anak-anak? Is this parallel or series reaction?
Parallel.
Yes, parallel. Okay, so this is a parallel. Okay, so desired product is, okay, so you have RD here. Okay, K1 CA CB, then we have a CA CB. Okay, so let's say lah, ni adalah 2A. Okay, and then we have another one which is SDU. Okay, remember SDU is RD over RU. Okay, so you just perkan dia, which is KCA2CB per dengan K2CACB. Okay, so you can cancel it here. Alright, what remain here is K1 K2CA. Okay, so to maximize the selectivity of D with respect to U, run at high concentration of A and use PFR. Okay, sebab apa? Okay, sekarang ni kita ada high, kita nak get a high selectivity, alright, with high RD and lower RU. Okay, so sekarang ni we have a K1CA, okay, 2CB, okay, over with the K2CACB. Okay, so this one cancel, cancel, cancel. And then what remain is K1CA, K2. Okay, means that kalau you tengok sini kita nak high ke atas kan. So means that kita nak dapatkan selectivity tinggi by having a higher concentration of A. Okay, so daripada situ kita boleh tahulah kita perlukan high concentration of A. Okay, so if katakan dalam case liquid, if liquid, alright, jangan guna diluent, alright. Dia punya salah satu solution dia untuk maintain high selectivity, don't use diluent. Diluent ni yang untuk cairkan lah, ataupun solvent lah. Kita mixkan solvent lain. Okay, sebab kita nak dapatkan high concentration of A. Okay, kita kena maintain of a high concentration of reactant A in order to get higher selectivity. Okay, but if gas pula, apa solutionnya adalah, okay, kita kena ada feed A at high pressure. Okay, sebab kenapa? PV is equal to nRT. Alright, P is equal to N over RT, so this one is CRT concentration. Okay, so kalau kita increasekan P, concentration akan increase. Okay, and then this one, do not use inert. Okay, so kalau you campurkan stream yang masukkan A plus with the inert, so dia akan jadi diluted lah. So bila dia diluted, concentration A akan rendah. So dia tak akan mencapai dekat high selectivity. Okay, so the best way is run at high concentration of A and use PFR. Okay, kalau CSTR kita boleh masukkan diluent. Okay, so that's why CSTR not preferable lah. Dalam case ni adalah PFR. Okay, okay, so nak rehat sekejap boleh? Kita ada 10 more slide saja. Kita rehat sekejap.
Boleh, madam.
You pergilah makan dulu ke apa. 10:45 kita berjumpa lagi, okay? Iklan slide. Alright. Okay, yuhu, dah ada ke semua orang?
Dah, madam.
Okay, alright. Kita continue
Madam.
sikit. Okay. Alright, so sekejap kita continue dekat 6 point. Okay, alright, so saya, kita pergi ke new ni. Sikit je lagi. Okay, Rectus selection based on selectivity and yield. Okay, so sebelum ni kita dah belajar lah secara amnya how to determine to know how to maximize the D. Okay, so now maksudnya sebelum tu kita dah dah go through lah, went through all the reaction type of reaction, multiple reactions. Okay, now is the topic of subtopic of Rectus selection. Okay, based on the selectivity and yield. Okay, so Rectus selection for parallel reactions, okay, depend on selectivity, okay, the yield, the temperature control, safety and cost. Okay, so this is the factors that you need to take into consideration lah when you what do you call it, when you want to select a reactor. Hari ni saya macam tak tahu lah kenapa saya tersasul je. Okay, so from here, okay, if you can see this is a CSCR, and then we have a tubular reactor ataupun PFR. Okay, dalam PFR ni pun dia boleh banyak tube dalam dia. Okay, dia bukan setakat single tube. It can be a lot of tubes, okay, within the reactor. And then we have a batch here. And then this is semi-batch. Okay, so semi-batch ni means that dia lebih kurang macam fat batch. Okay, we call as fat batch lah. Okay, fat batch ni means dia masukkan tapi dia tak ada keluar. Okay, dia semi, dia separuh sahaja. Okay, and this one. Okay, so let's say we have a A plus B product. Okay, two product. Okay, so kita tengok one by one. Okay, now we have a CA and also CB. Okay, so for this CSTR, if we can see there's a two inlet here, which is A and B. Alright, which means if there is a two inlet here, the CA, alright, and CB yang keluar sini akan jadi rendah. Okay, sebab dia ada diluent here. Okay, and for this one pula tubular reactor ni, okay, kalau kita ada A and B and kita increasekan pressure here, alright, we will have a high CA and also high CB. Okay, and so on lah. Okay, and for this one pula, kalau you tengok kita ada fat dia kepada B here, tapi dalam sini dah ada pure A. Alright, means that dalam sini sebenarnya CA dia adalah tinggi. Okay, CA dia tinggi, tapi CB dia rendah. Sebab kita masukkan B ni untuk cairkan dia, so CB ni adalah rendah. Okay, yang ni pula dia inverse to D ni, which is pure B dalam ni, alright, yang terhasil dia akan tinggi lah. Okay, tapi CA dia rendah. Okay, sebab dia kita nak kontrolkan dia, kita diluentkan dia. Alright, macam itulah dia punya konsep. Okay, alright. So for here, alright, if there is a, let's say if there is a side reaction, okay, okay, ataupun kita ada side stream, sorry, I nama side stream lah. Okay, use if we want low concentration. Okay, so we put another stream, kita panggil side stream sebab ni kita nak lowerkan concentration dia. Okay, that's why disebab itulah tujuan dia side stream. Okay, so for example, we have a here, kalau you tengok dekat sini kita ada side stream dia. We have a A and B. Okay, here kita ada stream lagi untuk B. Dia bukan satu sahaja, dia ada B masuk kat sini, here and here and here. Okay, so this we call as side stream. Okay, so daripada situ kita boleh rendahkan B lah, which is CA akan tinggi. Alright, CB akan rendah. Alright, sebab kita nak jadikan dia lower concentration. Kita instead of pure yang masuk, kita pecahkan dia stream dia. So dia akan rendah lah. Alright. Okay, so for here pula, dia terbalik pula. B akan masuk adalah pure. Alright, which is B akan tinggi lah. Okay, side stream dia dekat A. Alright, which is pecahkan dia jadi rendah. Okay. And then we have this one. Alright, a series of small CSTR. Kalau you tengok dia pecahkan B here. Okay, so means that CA yang produce ni dia makin lama makin tinggi lah. Sebab starting from here maybe conversion dia start from 50 and then conversion here start with 70 dan makin increase. And this one is 90%. Okay, so daripada sini CA akan tinggi, alright, and CB akan rendah sebab dia banyak side stream here. Okay, and for this one, okay, this one is applicable kalau you nampak sign ni means untuk heat lah, the supply heat. Remember tadi saya ada cakap yang dia adalah depends pada dua main factor K ni, constant dia ni, okay, which is depend on the temperature and also concentration. Okay, so kalau kita cover antara dua ni, kita boleh maintain the selectivity dia lah. Alright, so yang ni adalah applicable untuk highly exothermic lah reaction. Okay, ni control dari segi temperature. Alright, and then we have here we have a A and B. Alright, this is CSTR recycle. Okay, and then we have this one. Okay, this one kalau K dengan I ni, okay, let me. Okay, K and I ni lebih kurang kalau kita ada A plus B is equal to C plus D. Okay, dalam sistem ni sebenarnya dia adalah reversible. Alright, tapi kita nak kontrolkan dia ni supaya C ni remove. Okay, sebab apa? Kalau C ni ada, dia akan form balik ke A sebab dia reversible. Okay, so kalau you tengok gambar ni, C ni dia removekan, dia keluarkan. Okay, so this one is remove C for reaction to continue. Okay, so dia removekan C sebab C ni bila kalau ada kita usik pada macam mana cakap, kalau dia dalam reversible, so kalau kita tak removekan dia, dia boleh C ni convert back to the reactant. Okay, so kita tak nak. That's why kita kena removekan C tu. Alright, so this one dia apply to Le Chatelier lah. Le Chatelier. Ni macam yang topik number 5 tu lah, last tu. Principle. Okay, so you remove the C in order to get the D. Okay, so remove C so that C ni tak be convert back to A. Right? Then we have a reactive distillation. Okay, so reactive distillation ni sebenarnya you kena faham lah apa maksud konsep dia. Okay, kalau kita guna reactive distillation, katakan we have a acetic acid, alright, from H2O. We have a kita nak to remove acetic acid from H2O. Okay, so kalau kita guna reactive distillation, the separation of the product, may I tulis ni, separation of the product from the reaction mixture tu, okay, does not need a separate distillation step. Okay, so means that dalam ni dia dah boleh separate terus C dah. Okay, dia tak perlu go another unit operation in order to separate the C. Okay, itu dia kita panggil reactive distillation. Okay, dalam mixture ni dia dah boleh terus buang dah C. Okay, dia tak perlu have another independent unit lah in order to remove the C. Okay, so daripada situ kalau kita guna reactive distillation, sebenarnya dia lagi, cost dia lagi rendah lah. Cost akan rendah and save energy. Alright. So the PFR is used for gas phase reactions. Alright, and CSTR is used for liquid reaction. Allah, kenapa ni? Sekejap. Okay, sekejap. Okay, so reactor with recycle shown in 1 and J can be used for highly exothermic reaction. Okay, ni yang I tunjuk tadi lah, yang ada heater tu jugalah. Okay, alright, the recycle stream is cooled and returned to the reactor to dilute and cool the inlet stream, thereby avoiding hotspot and runaway reactions. Okay, for example, kita ada tadi lah, which is A and B masuk. Okay, single inlet masuk kat PFR here. Okay. Okay, then dia akan recycle back here. Okay, so dia cool down kan. Reaction yang keluar ni, liquid yang keluar sini ataupun gas yang keluar ni panas. So dia cool down, dia nak recycle back here. Okay, so dia tak adalah build up pressure here. Reactor K and L are used for thermodynamically limited reaction. Equilibrium lies for the reactant side. Okay, ni yang the one I show you lah, this one. Okay. And one of the product must be removed for the reaction to be continued. Okay, sebab kita nak reaction dia move forward saja. A plus B equals to C plus D. Okay, we don't want to become C plus D becoming back to A plus B. Okay, so the membrane reactor K is used for thermodynamically limited gas phase reactions. And reactive distillation is used for the liquid phase reaction where one of the product has high volatility than the other species of the reactor. Okay, so you boleh apply lah kalau ada difference in the volatility between these two product. Okay. Okay, so reactor selection. Okay, so we consider two simultaneous reactions in which two reactants A and B are used to consume to produce a desired product D and undesired product U. Okay, so katakan we have two kind of reaction. Okay, so the red law for the reaction of R, reactions R, okay, tengok pada RD. So RD is equal to K1 CA alpha. Okay, alpha ni bergantung pada order of reactions and CB beta 1. Okay, so alpha is for A species and beta for the B species. And for RU, okay, just put it as number 2 here. Okay, so for the red selectivity parameter, remember RD over RU. Okay, so you just equals to K1 CA CB ni, alright, over with this one. So automatically kalau you ada bawah ni, dia akan tolak lah, which is alpha 1 minus with the alpha 2. Okay, sebab dia per kan, and then we have a beta 1 minus with the beta 2. Okay, so you can simplify this equation to become like this one. Okay, so example, alright, we have a K1CA2CB and then RUK2CACB. Okay, so we can cancel this one, become CA1 and then this one dah habis lah. So K1 over K2CA. Okay, so to maximize the selectivity of D, okay, nak maximizekan dia. Alright, with respect to U, run at high concentration of A and use reactors such as B, D, F, H and in figure 6.3. Okay, dalam ni tak ada figure pula, tak apalah. Tapi yang pasti, you faham kan konsep dia. So sekarang ni kita kena tinggikan CA. Okay, so untuk tinggikan CA, yang sesuai adalah untuk guna PFR. Okay, kita nak CSTR lah. CSTR tak perlulah sebab kita tak perlu diluent. Okay. Okay, so example 6-3, alright, from the formula. Okay, kita akan kaji one by one case, alright, by looking at the alpha here. Okay, sekarang ni kalau selectivity, you tengok pada alpha punya case by case. Okay, so for the parallel reaction, we have two kind of reactions. Consider all possible combination of reaction orders and select the reaction scheme that will maximize STU. Okay, so from here you can analyze what is the best option of the reactor selections to maximize the STU. Okay, so daripada sini you kena kaji one by one the reaction order. Okay, for example, for case number 1, we have, katakan kalau alpha 1 is more than alpha 2. Okay, katakan kalau the rate of the order of reaction alpha 1 ni lebih tinggi daripada alpha 2 and also beta 1 lebih besar dari beta 2. Okay, kita tengok dulu case one by one ni. Okay, I faham you takkan 100% faham lah, tapi nanti slide lepas ni saya akan terangkan one by one. Okay, and then we have a second one. Let's say kalau alpha 1 ni pula lebih daripada alpha 2 tapi B1 less than beta 2. Okay, so kita define as case number 2. And then let's say number 3 pula, alpha 1 less than alpha 2, alright, and beta 1 is less than beta 2. Okay, so kita just assign as case 3. Kita tengok satu-satu tau, kita nak tengok kalau ni besar, ni kecil macam mana, ni besar, ni kecil macam mana, okay. Alright, so sebenarnya ada 4 probability lah yang kita boleh tengok daripada sini. And then another one, the fourth one would be alpha 1 less than alpha 2, but the beta 1 is higher than beta 2, which is case number 4. Okay, so I will go through one by one. Okay, so kalau tak faham, interrupt je saya. Okay, so kita tengok pada case number 1. Okay, let's say the alpha 1 here, okay, katakan this one 2, alpha 2 ni kosong. And beta 1 is larger than beta 2. Alright, so we have just defined as A is equals to A alpha 1 minus with the alpha 2, and B is beta 1 minus with the beta 2. Okay, just assignkan dia lah untuk tolakkan dia atas tolak bawah. Okay, ni pun atas tolak bawah. Okay, so daripada situ kita positionkan balik, which is this one kita dah summarizekan tadi. Okay, sebab apa? A ni adalah sebenarnya alpha minus alpha 2, and this one is B ni adalah beta 1 minus beta 2. Okay, kita simplifikan dia A dengan B. Alright. So daripada sini kita nak maximizekan SD. Okay, remember tujuan kita lah untuk maximizekan SD. Okay, sekarang ni kita tengok pada syarat dia, alpha 1 ni kena lebih besar daripada alpha 2, beta 1 ni kena besar daripada beta 2. Alright, means that, okay, saya tulis balik semula, SDU is equal to RD over RU, okay, is equal to K1 CA alpha 1 CB beta 1 K2 CA alpha 2 CB beta 2. Alright, so in order for increase here, kita dah tulis dah kat sini, ni lebih besar yang bahagian atas ni, sebab alpha 1 lebih besar di bawah, beta 1 lebih besar dari beta 2. Okay, which is kita kena increasekan CA and kita kena increasekan CB. Okay, so daripada sini apa kita kena buat? Kita kena maintain the concentration of both A and B as high as possible. Inilah kita nak maintain yang atas ni. Alright, so what are the choice is using a tubular reactor, okay, and then batch reactor. Okay, sebab batch reactor kita boleh maintain lah sebab kita composition inside of A and B dalam ni sebab kita tak usik inlet and outlet. Okay, tubular reactor pun kita boleh as a continuous operation. Okay, and this one is high pressure lah if gas phase. Okay, so kita boleh guna high pressure untuk maintainkan dia high CA and also high CB. Alright, and jangan guna inerts lah sebab kita nak, kalau boleh try to reduce inerts. Alright, okay, get it everyone? Okay, ini untuk case. Kalau liquid pula, if liquid, do not mana saya punya ni? Kalau untuk liquid pula, do not use diluent, alright, ataupun solvent. Okay, so this is applicable for liquid. Okay, inilah dia punya cara untuk maximize the selection. Okay, then we have another one, which is case dia alpha 1 lebih daripada alpha 2, but beta 1 is less than beta 2. Alright, which means that, okay, we have a K1 over K2, which is CA alpha 1 minus with alpha 2, CB beta 1 minus beta 2. Okay, so daripada sini we should know that boleh simplifikan lah, K1 over K2 CA ni CB. Alright, so which means that from here we want to make the concentration of A high and the concentration of B low. Alright, sebab B tu ni lebih rendah, So dia akan jadi minus. So dia akan remain kat sini bawah. Okay, so automatically ini akan kena tinggikan, ini kena rendahkan. Okay, sebab sini adalah alpha 1 lebih daripada alpha 2. Alright, and this one is beta, what do you call it, beta 1 less than beta 2. So bila beta 1 ni adalah lebih rendah, okay, katakan this one is 1, beta 2 is 2. So 1 minus 2 is minus 1 kan? That's why alpha B tu dia dekat bawah. Sebab dia minus. Kalau positif kat atas lah. Alright. So automatically daripada sini you kena tengok kita kena rendahkan B tapi kita kena maximizekan A. Okay, macam mana adalah tengok balik daripada yang sebelum ni figure, which is kita boleh guna fat batch ataupun semi batch. Alright, which is B kita fed slowly tapi dalam sini maintain a pure A. Alright. And then a membrane reactor or a tubular reactor with side stream of B continually fed to the reactor. Okay, so salah satu caranya kita guna banyak side stream untuk B. Sebab kita nak rendahkan CB. Alright. Or a series of small CSR with A fed only to the first reactor and small amount of B fed to the each reactor. In this way, B is mostly consumed before the CSR exit stream flow into the next reactor. Okay, so daripada situ kita boleh guna juga a series of CSCR. Okay. Alright, whereby A sahaja is being fed into this reactor. Alright, tapi on the same time B pun kita fed tapi dalam small quantity. Okay, so bila dah habis reaction ni convert, B dah tak terkeluar dah. Okay, sebab dia dah mostly consume dah. Okay, so yang keluar akan jadi A lah, yang tinggi A. Alright, so this is how we maintain. Okay, sebenarnya benda ni adalah logical lah. Benda yang macam logik lah untuk difikirkan. Okay, cara dia. Refer je dekat satu figure yang figure ni. Alright, cuma you adjustkan dia macam satu A. Kalau tinggi macam mana, B rendah macam mana. Macam tu je lah. Okay. Another one. Okay, this case is alpha 1 is less than alpha 2. Beta 1 is less than beta 2. Okay, kalau less, automatically dia akan jadi negatif lah dua-dua ni untuk A and B. Okay, so bila dia jadi negatif, kita perkan dia ke bawah. Okay, so we have a K1, K2, CA, CB. Okay, now kita nak maximizekan SDU. Okay, so bila kita nak maximize, of course yang value bawah ni kena rendah lah. Okay, so automatically what we need to do is we need to have a low CA and low CB. Alright, so macam mana nak guna low CA and CB? Kita kena guna CSCR lah. Alright, so CSCR ni kita boleh letak dilute. Dilute the concentration of E and B. Okay, so kita boleh dilutekan lah, masukkan dia A and B here, kita dilutekan dia, kita cairkan dia. Alright, ataupun a tubular reactor in which there is a large recycle ratio. Okay, ataupun kita feedkan dia dengan inert, kita dilutekan inert, and ataupun this one is for gas phase. Okay, ataupun kita buat dia at a low pressure. Alright, gas phase ni kena low pressure. Alright, in order for you to get this one. So meaning that sekarang ni adalah A is equal to alpha 2 minus with alpha 1. B is beta 2 minus beta 1. Okay, so daripada situ adalah K1 over K2. CA alpha 1 minus alpha 2. Okay, CB beta 1 minus beta 2. Okay, so daripada situ actually is equal to K1 over K2. CA minus A. Alright, and CB minus B. Okay, that's why dia jadi turun ke bawah sini. Alright, kalau you nak jadikan dia, that's why kalau asal dia kan alpha 1 minus alpha 2 A kan, tapi sekarang ni kalau letak A2 sini, automatically dia akan jadi terbalikkan. Kalau you terbalikkan, jadi A is equals to A1 minus alpha 2 and minus B is equal to what do you call it, beta 1 minus beta 2. Terbalikkan dia saja. So Yang asalnya macam ni kan. So sorry, ni beta 1 minus. So bila you jadikan ni, dia jadi minus lah kat sini. Alright, sebab dia lebih besar. Okay, and then we have another one. Okay, alpha 1 is less than alpha 2. Alright, and beta 1 is bigger than beta 2. Means that bila bigger, dia akan jadi positif. Atas dia, yang ni akan jadi negatif. Okay, so automatically CA ni akan turun bawah lah. Ni CB kat sini. Okay. So daripada situ, you akan dapat macam mana nak tinggikan SDU ni. SDU ni you kena rendahkan CA tapi tinggikan CB. Right, which is at high concentration of B and low concentration of A. So yang paling okey adalah guna semi-batch reactor. Okay, so semi-batch reactor dalam ni pure B. Okay, tapi kita masukkan small amount of A. A here. Alright, a membrane reactor to a tubular reactor with side stream of A. Okay, yang ni kita gunakan banyak side stream of A, nak dilutekan dia. Ataupun a series of small CR with fresh A fed to the each reactor. Okay, so nanti bila keluar exit reactor yang second, dia dah berkurangan dah CA ni. Okay, sebab dia dah convert dah A setiap dalam reactor ni. Okay, so in this very important example, we show how to use the instantaneous selectivity SDU to guide the initial selection of the type of reactor and reactor system to maximize the selectivity with respect to the desired D. Okay, so the final selection should be made after one calculate the overall selectivity for the reactors and operating condition chosen. Okay, that's why you kena summarizekan dulu macam ni dulu, baru you boleh tengok reactor selection mana yang sesuai and nak perlu manipulate macam mana untuk concentration of A and B. Okay, in order for you to maximize this one. Okay. So far okay ke?
Okay, doktor.
Alright, okay. So yang lain ni dia macam summary dia macam tadi yang saya ajar. Okay, so you boleh tengok one by one. Macam itulah. Okay, so saya rasa itu sahajalah for today. Boleh kita end our class today?
Boleh, doktor.
Boleh.
So you all prefer tutorial nanti kita buat masa habis semua semua topik ni ke, atau you nak buat minggu ni pun nak tutorial juga? Half-half.
Ikut doktor ke?
Sebab kadang ada student ada your own ni kan choice, tapi tak apalah, saya rasa better saya bagi soalan awal tapi kita discuss untuk the next week lah. Okay, so that you have ample time lah. Okay, so for the next one nanti saya akan kita akan buat banyak exercise juga. Saya akan bagi slide dia sama ada hari ni atau esok for the Thursday punya lecture. Okay, okay, so saya rasa itu sahajalah. Okey ke kita habis awal hari ni? Saya malas nak apa?
Okey je, doktor.
Malas nak apa macam compress sangat sebab lagi pun ini macam new. So elok saya macam slow sikit lah. Yang ni untuk perkenalkan dulu konsep dulu dengan prinsipal dia lah, multiple reactions. Okey, saya tak naklah rushing. Nanti bila rushing pun you akan jadi confused. So better saya go one by one lah. Alright, sebab lagi pun yang week sebelum ni saya banyak macam terpaksa compress sebab kita ada 2 kali cuti masa tu. Okey, dan saya rasa macam tak sedap lah, unethical lah kalau saya nak buat kelas even though public holiday. Benda tu macam tak sesuai lah sebenarnya. Okey, so saya rasa itu sahajalah, kita end our class with Al-Fatihah and surah to us. Okey, sebelum tu saya lupa nak buat announcement. Nanti minggu ni saya akan bagi assignment number 2 is a group assignment. Okey, maksimum 3 orang sahaja. Sebenarnya saya nak buat 4 orang tapi dibangga tak boleh. Course coordinator kata kena buat 3 orang juga satu group. So nanti is a mini project lah. So you kena buat in a group. Nanti saya akan bagi maybe hari Khamis kot soalan dia. Alright, and untuk final assessment ni, you try lah concentrate nanti chapter 5, 6 and 7. Okay. Dia sebenarnya link juga dengan set chapter sebelum tu. Cuma maksud saya supaya awak betul pastikan yang awak betul-betul faham lah untuk setiap topik yang 3 tu. Penting tu. Alright. Okay, so itu sahaja. Jumpa hari Khamis ya.
Okey. Terima kasih doktor.
Thank you, doktor.
Alright.
Thank you, doktor.
Assalamualaikum.
Thank you.
Salam.
Adios. Bye.